Good morning, everyone. We are Group 3, and today we will present our case study on the modified PJM 5-bus model. Next. Here is our group members. My name is Hou Guanting, metric number 218410.
Hello everyone, my name is Zhang Junhao, and my metric number is 218633.
Hello everyone, my name is Guo Zhaonian, my metric number is 218400.
Hello everyone, my name is Lin Zhongsen, and my metric number is 218471.
Okay, now let's start with the brief introduction. Our project is inspired by a PJM interaction. This is a massive electronic grid in the eastern US, and we closed this model for a good reason. It is complex enough to show the real grid behaviors, and it also small enough for the clear manual calculation. Next. And moving to the system overview, we are analyzing a 230 kilovolts 5-bus network based on the Met Power Case 5. The base power is 100 megawatt amperes, and the base voltage is 230 kilowatts. For the topology, bus 1 is a stock bus, bus 3 and bus 5 are generator bus, and bus 2, bus 4 are load bus. They are connected by a total of 6 transformation lines. Next. So our network analysis has 4 main steps. First one is we internalize the per unit system. Second, we convert the branch parameter. And the third, we build the Y-bus metric. Final, we compute the metric reduction. Next. Step 1 is the base calculation. We use the give 100 megawatt amperes and 230 kilowatts. From this, the base independence is 529 ohms, and the base and maintenance is 0.001890 Siemens. This creates a on-fide framework. It standardizes parameters and simplifies our calculation. Next. Step 2 is the parameter conversion. We converted the several independence into several and maintenance for all 6 lines. We also found the charging dependence at both ends and at both ends of each line. These values are basic building blocks for our system metric. Next. Step 3 is the building the Y-bus metric. Yes, and we calculated the diagrams terms first. This response self and maintenance. We summed all admittance and charging suspendence connected directly to the bus. Next are the off diagram terms. All manual admittance. This is just a negative or several admittance between two connected buses. If buses are not connected, the value is 0. Next. Here is our final output. We successfully built a 5x5 complex Y-bus metric, and this metric responds the whole grid topology. It is a mathematical foundation for any future power flow analysis. And here's all my part. Next.
So now I will present the power flow analysis section of our modified PJM 5-bus power system. The purpose of this analysis is to evaluate the steady state operating condition of this system. In this part, we focus on bus voltage magnitude, a voltage angle, generator power output, loader condition, line power flow, and line losses. So this analysis helps us check whether the system operates normally, whether the voltage profile is acceptable, and whether any transmission line becomes overloaded. Next. So this slide shows the bus classification and schedule power data. So bus 1 is a slack bus, which provides the voltage angle reference and balances the system power losses. And bus 2 and bus 4 are PQ buses, meaning their real and reactive power are specified, where their power magnitude and angle need to be solved. So as for the bus 3 and bus 5 are PV buses, which are generator buses. Their real power and voltage magnitude are specified, where active, reactive power and voltage angle are calculated. Next. So this slide explains the network model using the power flow calculation. The final Y-bus metric from network analysis is used directly here. It represents the electrical connection between all buses, including line impedance and charging admittance. The network includes 6 transmission lines as follows. The formulas show the relationship between bus voltage, current injection, and complex power. The main idea is simple. The bus voltages and Y-bus metric are used to calculate power at each bus. Then the calculated power is paired with the scheduled power to get a mismatch. Next. So this slide shows the Newton-Raphson method used to solve the power flow problem. The unknown variables of the voltage angle of bus 2 to 5, and the voltage magnitudes of the PQ bus, which are bus 2 and bus 4. For the PV buses, bus 3 and bus 5, the voltage magnitudes are fixed at 1 per unit. The process is interactive. First, the method calculates the power mismatch. Then the Jacobi matrix is used to update voltage magnitude and angle. This continues until the mismatch becomes very small and the solution converges. Next. So this slide presents the final bus voltage result. From the table, all bus voltages remain close to 1 per unit. So the overall voltage profile is acceptable. Bus 1 remains at 1 per unit and 0 degrees because it's the slack bus. Bus 2 is 0.9893 per unit, and bus 3 remains at 1 per unit. Bus 4 has the lowest voltage at 0.9813 per unit, and bus 5 remains at 1 per unit. The key finding of this bus 4 has the weakest voltage profile. This is reasonable because power 4 is the largest PQ load bus, so it has a larger voltage drop. Next. So this slide shows the final generator power output. Generator G1 at power 1 produced 215.34 megavolts and 91.92 power watts. Since bus 1 is a slack bus, its output adjusts to balance the system load and losses. So the important point of that is all the generator reactive power output within their limits. Therefore, the generator option is acceptable, and the PV buses can maintain their voltage magnitudes. Next. So this slide is the main power flow results diagram. The arrows show the actual real power flow direction. For example, power flow from bus 1 to bus 2 through L12, from bus 1 to bus 4 through L14, and from bus 5 to bus 1 through L15. This line labels show the complex power flow and line losses. This allowed us to see both the direction of power transfer and the loss on each line. So the key results show that the total real power loss is 5.34 megavolts, and the total reactive power loss is 45.79 megavolts. The most important result is that line 45 has the highest loading, about 102.21%, which means it's slightly overloaded. Next. So this slide summarizes the result. Overall, the bus voltage profile is acceptable because all voltage magnitudes remain close to 1 per unit. The total real power loss is 5.34 megavolts, which means the system operates efficiently under the studied condition. However, line 45 is slightly overloaded with a loading of 102.21%. Therefore, line 45 is identified as a critical transmission line. Possible improvement actions include generation redispatch, load redistribution, or of the line 45. Overall, the system can operate under the studied condition, but line 45 should be monitored carefully. So that's all my part. Thank you very much.
I will present the fault analysis and the stability assignment of the modified 230 kilovolt 5-bus transmission network. This part focuses on 3 aspects: 3-phase solid fault analysis, pre-disturbance stability assessment, and the critical bus identification. The 3-phase solid fault is selected because it is the most survivable balance of fault. It helps us estimate the maximum fault current and check whether the protection system is suitable. Next. Next. This slide shows the system data used in the analysis. Bus 1 is a slack bus, so it acts as the reference bus and balances the system power. Bus 3 and bus 5 are generator buses, while bus 2 and bus 4 are load buses. This bus classification is important because each bus type has a different role during fault calculation and stability evolution. Next. Bus 4 is selected as the critical bus for fault analysis. There are three reasons. First, bus 4 has the lowest voltage magnitude, so it has the weakest voltage profile. Second, bus 4 has the largest load demand in the system. Third, it is a PQ load bus, which means its voltage is more sensitive to disturbances. Therefore, fault at bus 4 can strongly affect the system operation and is suitable for critical disturbance analysis. Next. In this analysis, the three-phase solid fault is applied at bus 4. For solid fault, the fault impedance is assumed to be 0. This creates a worst-case condition because there is no additional impedance to limit the fault current. The fault current is calculated using the pre-fault voltage and the equivalent impedance at the fault point. Next. Here's the fault current calculation. This slide shows the final fault current calculation. After substituting the values into the formula, the three-phase fault current at bus 4 is 18.42. This value is important for protection design. The circuit breaker must be able to interrupt a current higher than this value with the proper safety margins. If the breaker rating is too low, it may fail to clear the fault safely. Next. This table compares the fault current at different buses. Bus 2 has 13.12, bus 3 has 11.82, bus 4 has 18.2442, and bus 5 has the highest value, 43.97. Although bus 5 has the largest fault current, bus 4 remains the main focus because it is the biggest load bus. From the protection point of view, the breaker rating should be higher than the calculated fault current, especially at critical buses. Next. For stability assignment, the generator bus angles are considered. Bus 1 is the reference bus, so its angle is 0 degree. Bus 3 has an angle of 3.826 degrees, and the bus 5 has an angle of 0.836 degrees. Angle difference between generator buses is small. This means the system is still stable before the disturbance. Also, the minimum voltage appears at bus 4, which again confirms the bus 4 is the biggest bus in the system. Next. This slide shows the generator output condition. G1 produced 215.34 and 91.92. G3 produced 323.49 and 257.91. G5 produced 460.51 and 24.65. All generators are within their reactive power limits, so there is no limit violation. The system can apply the total load and the real power is lost in 5.34. This shows the system is operating normally before the fault. Next. During the bus fault, the bus voltage drops. When voltage of the electrical power transfer also decreases. At the moment the mechanical input power becomes greater than the electrical output power. As a result, the generator rotor and the rotor angle may increase. If the fault is not cleared quickly, the system may lose stability. Therefore, fast fault clearing, suitable breaker rating, and the proper protection coordination are necessary to maintain system stability of the bus for disturbance. Here's all my part.
Okay, and this is the conclusion. For this part, we summarize the key finding of the modified PJM 5-bus systems. First, the Y-bus matrix was successfully constructed to the response to the overall network technology from the power flow of the analyze. All bus voltages remain close to 1 per unit, which means the voltage profile is acceptable. However, bus 4 has the weakest voltage condition with a voltage magnitude of the 0.98113 per unit. The total real power loss of the system is the 5.34 megawatt. And in addition, line L45 is slightly overloaded with a loading of about 102.21%. For the funds, analyze the three-phase solid faculty current at bus 4 is the 18.42 kiloamps, while the maximum faculty current across at bus 5 with a value of 45.97 kiloamps. Finally, the system is stable under the per disturbance operating condition, but bus 4 is the most critical disturbance location because it has the lowest voltage and the largest load. And for the final statement, the modified PJM 5 bus network operates with an acceptable voltage and generation condition. The power flows results show that all bus voltage remain close to 1.0 per unit. The total real power loss is the 5.34 megawatts. This indicates that the system operates efficiently under the study condition. Therefore, possible improvement action include generation redispatcher, load management, reactive the power support, protection coordination, and the network reinforcement. This action can improve the reliability and security of the modified PJM 5 bus network. Thank you. Okay, this is our reference. Okay.